Welcome to another explainer. Today we're looking at something absolutely fascinating that's happening right under your fingertips. Think about the device you're using to watch this right now. Inside it is a microchip, right? Well, I want you to imagine that microchip not just as a flat piece of silicone, but as a bustling, hyperdense miniature city. And just like any massive metropolis, if you don't have roads, traffic lights, or rules of the road, the whole thing grinds to a complete, disastrous halt. So today, we're tracing the evolution of VLSI communications and different protocols. We'll see exactly how this microscopic infrastructure went from simple dirt roads to a crazy, complex, packet-based digital metropolis.
Okay, so in the world of very large-scale integration, or VLSI, protocols are basically the communication standards for transferring data between different blocks on a chip. You can really just think of them as the critical traffic laws that keep a microchip from experiencing total gridlock. They make sure data exchange is reliable, synchronized, and incredibly efficient. Because honestly, without these protocols, the processor wouldn't even be able to talk to the memory, and your device would just be a very expensive paperweight.
Here is our roadmap for the explainer today. We'll cover 1. The basics of VLSI protocols, 2. The shared bus era, 3. The need for speed, 4. Off-chip and memory evolution, and 5. The network-on-chip revolution.
Let's kick things off with Section 1, Basics of VLSI Protocols and the Early Era. Tracking this evolution over 4 decades, we can see exactly how chips scaled up in complexity. We start way back with the shared bus in the 80s, move into the structured AMBA architecture in the 90s, step on the gas with AXI performance in the 2000s, and finally land on the highly complex network-on-chip in the 2010s. And you know, every single step of this evolution was forced by one massive problem. Chips were just getting too complex, and the old tragic laws simply weren't cutting it anymore.
So let's look at that very first step, the early shared bus. Imagine our microchip city as a tiny one-stop light rural town with just a single main street. Everything, the CPU, the memory, the peripherals, was hooked up to this one common bus. Take the early Intel 8086, for example. The golden rule was that only one device could talk at a time. Now, this worked totally fine when chips were small, but as things scaled up, you suddenly had multiple devices fighting to use that one road. This contention caused terrible traffic delays. Plus, physically long wires meant awful signal lag. We definitely needed a better city plan.
Moving right along to Section 2, the shared bus era grows up.
To solve that ridiculous Main Street traffic jam, a huge development happened in the 90s when ARM introduced the AMBA architecture, that's Advanced Microcontroller Bus Architecture. Instead of one shared road, AMBA cleverly split the system into dedicated domains. They built AHB, the Advanced High Performance Bus, to serve as the high-speed highway. Then they built APB, the Advanced Peripheral Bus, to act as the local, slower roads for low-power peripherals. This separation was a total game-changer. It improved performance, sure, but it also enabled modular design. For the first time, engineers could easily reuse standard IP blocks across the industry.
Which brings us to Section 3, the need for speed.
By the early 2000s, systems on a chip were getting incredibly powerful, and latency was becoming a serious bottleneck all over again. Enter AXI, the Advanced Extensible Interface. AXI solved these bandwidth issues by breaking data transfers down into highly efficient simultaneous steps. Step 1 introduced parallel channels, so you could read and write data at the exact same time. Step 2 allowed for burst transfers, letting you send big chunks of data super efficiently. And Step 3 utilized pipelining and out-of-order transactions. Basically, instead of waiting for one single delivery truck to finish its whole route before sending the next one, AXI let multiple trucks constantly stream down the highway, keeping traffic flowing and maximizing throughput.
Now let's jump to Section 4, Off-Chip and Memory Evolution.
While the inside of the chip was evolving at breakneck speed, off-chip communication was going through its own revolution. In the early days, talking to external devices or sensors relied on older, pretty slow serial standards, like UART or I2C. But to achieve better signal integrity and raw speed going off-chip, the whole industry aggressively shifted to high-speed serial links. Think PCI, USB, and Advanced Ethernet. This shift was massive because it meant our microchip city could now import and export huge amounts of data to the outside world without skipping a single beat.
And of course, we absolutely cannot talk about off-chip communication without talking about memory. Historically, memory has been the biggest bottleneck of all. The CPU is crazy fast, but if it has to sit around waiting for data from memory, the whole system lags. This drove an evolution focused relentlessly on higher bandwidth and lower power. We went from standard SDR to DDR all the way up through DDR4 and DDR5 today. We also saw specialized branching. LPDDR became the gold standard for keeping power consumption super low in our mobile phones, while HBM, high bandwidth memory, was created for high-performance systems that just demand raw, unadulterated speed.
Finally, we reach Section 5, the Network-on-Chip Revolution.
The ultimate paradigm shift in VLSI protocols happened when we simply hit the laws of physics. The traditional bus is centralized. It relies on dedicated wires. Even as a structured highway, it has physical limits when you've got dozens or hundreds of cores all trying to talk at the exact same time. The modern solution? The network on chip, or NOC. NOC is literally an internet inside the chip. Instead of dedicated wires tying everything together, data is packaged up and routed through a distributed, scalable network of internal routers. This parallel communication slashes congestion and is exactly the architecture powering today's most insanely complex GPUs and AI processors.
So let's recap this whole incredible story. In the 1980s, the shared bus gave us that basic connectivity. In the 1990s, AMBA brought in much-needed structure and modularity. By the 2000s, ACI and PCIe arrived to deliver high performance and off-chip speed. And then the 2010s brought us NOC to solve the ultimate problem of scalability. Every single era-specific bottleneck birthed a faster, smarter protocol. We evolved from shared to dedicated, parallel to high-speed serial, and finally, from a simple bus to an entire on-chip network.
So, to bring it all together, why does this actually matter to you? Well, these microscopic traffic laws are executing billions of times a second in the device you're holding right now. Thanks to these standardized protocols, engineers can leverage modular design. They don't have to reinvent the wheel for every new chip. They can just reuse proven IP blocks. It ensures compatibility, improves massive scalability, and fundamentally keeps the overwhelming complexity of modern chip design from spiraling completely out of control.
Which leaves us right here. The network on chip is the absolute pinnacle of current design, a literal internet inside a chip. But as physical limits get pushed to the absolute brink by modern, power-hungry, exponentially complex AI processors, how on earth will this internal infrastructure evolve next? What actually comes after the internet inside a chip? It is a fascinating question, and I'm going to leave you with that to ponder. Thanks so much for joining me on this explainer, and as always, keep your curiosity switched on.